When finite element analysis fundamentally expands across a two-dimensional plane, the governing mathematical rules undergo a massive shift. In a one-dimensional bar, you interpolate linearly from point A to point B. On a two-dimensional plane, you have to map discrete nodal values across an entire continuous surface. Our objective here is to derive a continuous mathematical function, f of xy, that governs a single rectangular element. We must build this entire field knowing only the exact values at the four distinct corner nodes. Moving from a line to a continuous plane requires replacing straightforward linear paths with bilinear polynomial interpolation. This alters the underlying geometry of the element. We start by placing a generic four-node rectangular element into a standard Cartesian coordinate system. Looking at the bottom left, we anchor node 1 at the origin point, 0, 0. Moving along the x-axis, node 2 is at AB. Up in the first quadrant, node 3 sits at AB. Finally, node 4 closes the rectangle at 0, B. Establishing these four absolute coordinate pairs provides the mandatory physical boundaries before any polynomial equations can be applied. To find the right polynomial, we use Pascal's triangle as our architectural blueprint. We apply the rule of nodal parity. Because our element has exactly four discrete nodes, we need exactly four mathematical terms. Extracting from the top, we select the first four terms, 1, x, y, and xy. Combining these gives our baseline function. F of x, y equals a0 plus a1x plus a2y plus a3xy. The a values, a0 through a3, are unknown coefficients that we need to calculate. The x and y variables represent the spatial coordinates anywhere inside the boundary of the element. We convert this linear equation into matrix form. F of x, y equals row vector h times column vector a. Row vector h isolates the variable spatial coordinates. Column vector a groups the mathematical unknowns we are solving for. This generic polynomial has the theoretical capacity to model a flat plane, but right now it lacks the specific dimensions of our rectangle. To calculate our unknown coefficients, we force this generic equation to perfectly match the known values at the four physical corners. In the matrix formulation, node 1's 0, 0 coordinates leave only the 1. Node 2 at A0 keeps the A term. Node 3 at AB populates every variable in its row. Node 4 at 0B retains only the B variables. This newly populated 4x4 block is the coordinate matrix, denoted mathematically as T. This gives us the complete system of equations. Matrix T times vector A equals vector F. By enforcing these boundary conditions, the T matrix acts as a mold. It permanently encodes the exact dimensions of the rectangle, A and B, into the mathematics. Currently, our equation is solved for the nodal values, vector F. But we need to isolate the unknown coefficients in vector A. In linear algebra, to isolate a variable, the matrix must be inverted. We take coordinate matrix T and convert it into T inverse. This isolates our unknowns. Vector A is exactly equal to T inverse times vector F. Expanding this inverted matrix reveals significant mathematical complexity, introducing exact fractions like 1 over A and negative 1 over AB. We take this large inverted expression and substitute it directly back into our original generic polynomial. This derivation culminates in the final field equation, f of xy equals the row vector n times vector f. This inversion and substitution process successfully marries the abstract spatial coordinates with the hard geometric limits of our specific rectangle. Looking at the derivation, this tall column vector represents the four Lagrange interpolation functions, commonly known as shape functions. These four equations act as spatial weights. They determine exactly how much influence each corner node exerts on any given point inside the element. They all obey a strict mathematical law, the Kronecker delta property. The first half of this property states that a shape function must evaluate to exactly 1 at its designated home node. The second half dictates that the function must simultaneously evaluate to exactly 0 at the other three nodes. To test this property, we isolate the third function in the vector, n3, which equals x times y divided by a times b. These matrix formulas dictate the topographic behavior of the element's interior through rigid geometric rules.
This 3D surface plot translates the abstract math of N3 into physical topography. If we substitute the coordinates for node 3, A and B, into the formula xy over AB, the result is AB over AB, perfectly yielding 1. The peak on this graph confirms that the elevation at node 3 reaches exactly 1. Evaluating the math along the x and y axes shows that anywhere x equals 0 or y equals 0, the entire formula immediately collapses to 0. Geometrically, this guarantees the elevation is flat 0 at the locations of nodes 1, 2, and 4. Between these extreme points, a continuous warped gradient bridges the gap. This is the visual result of bilinear interpolation. We have taken 4 isolated, discrete data points and successfully derived a continuous, predictable mathematical field. Combining Pascal's triangle and matrix inversion, we sculpted a mathematically sound surface. This strict process provides the groundwork for stiffness matrices in two-dimensional FEA software.